Hello, everyone, and welcome to Lean for Scientists and Engineers. And my question for you is, how would you like to not just find and correct bugs in your code, but write code that's provably free of bugs? Okay? This might sound too good to be true, but I hope that by the end of this, you'll see some of our vision and how we're actually getting this to work. And this is going to be the first lecture in a whole set of lectures on how to do this. Today is going to be a main big vision talk and a little bit at the end about installation and starting to do proofs in Lean. Over the coming weeks, though, we'll be really digging into the details of how do we write proofs, how do we write programs in Lean, and how do we connect all of this to the domains of science and engineering. I'm Tyler Josephson. I run the AI and Theory-Oriented Molecular Science Lab, the Adams Lab at UMBC, and I'm really excited to share this work we're doing with you. So here's a high-level setup of what we have in store. We have 3 overall goals to cover in this course. We want to teach scientists and engineers a rigorous way of approaching logic and proofs. And that involves introducing people to theorem proving. I never took a theorem proving class. I never did a formal proof apart from like the geometry stuff that I did in high school. Once I got to college, I did the regular calculus and statistics, linear algebra, differential equations, and stopped essentially with my math training. That's all we need for typical engineering. But if you were a math major, then you would end up going a little bit further and you would learn how to do proofs. And we need proofs for this. So we're going to cover the basics, essentially, what I've distilled into as sort of a minimal set of things to kind of get scientists and engineers started. There's resources written for people getting majors in math, essentially, to go a lot deeper. If you're taking the proofs course, you can go a lot deeper into this. Our goal for this is to formalize derivations in science and engineering, improve properties about code that would be used to solve science and engineering problems. So the next section of this is functional programming in Lean. And if you've ever written some code before, you've typically done things with Python or C or Java. These are all imperative programming languages. Lean is a purely functional programming language, which just makes it different. And so we'll learn about those differences, and we'll learn about numerical versus symbolic mathematics and just how to write executable programs in Lean. And we'll combine all of these ideas together to enable us to write provably correct programs for scientific computing. So this is the tentative schedule. Welcome, you're here for day 1, and we're going to be doing an introduction to Lean and proofs and how that connects to science and engineering. The next 5 lectures over the first 3 weeks of this course will be about logic and proofs for science and engineers, and we are very closely following the content in Mechanics of Proof by Heather Macbeth. I highly recommend this textbook. You'll find it online. We get a lot of inspiration from that, but we're not using her examples particularly because for some different reasons. Okay, and also because we want to try to tie our examples to applications in science and engineering. The second half of this is going to be about functional programming in Lean, which there's another textbook on this. This one is going to teach us how to write executable programs. You need to be able to import data, do stuff with it, print it back out again. And there's nuances of here that we'll definitely talk about later. Both of these are full-length textbooks that you could study for an entire semester. We are doing a short version of the course here, so we're just sort of getting little snippets from each of these and bringing them together. And along the way, there's plenty of opportunities for you to go off and learn more, go more in depth into the content. And finally, we bring these together. We have a few different projects that we're doing in our lab. with BET analysis and molecular dynamics. And we also have a guest instructor, Tomas Scriven, who's been working with Lean for a while, and he has developed Silene. We'll be doing a tutorial on the thing he's building there. And that's the overall structure. So the schedule today is these 10 items. We have a lot to cover, but we have 2 hours. So here we go. Provably correct scientific computing. We really need to talk more about what I mean here, why we care about this, what's relevant for this. And I want to first bring up this paper. You may or may not have heard about this. This was published in March 2020, shortly after the COVID pandemic was setting in. And a way to describe this was they were running software that's essentially SimCity, but without the graphics. They're trying to model how different people would interact with each other. And if you have a group of these people who are sick with COVID-19 and they interact with other people and they make those people sick, and you model a city, you model a population of people in this way. And they were testing non-pharmaceutical interventions, aka lockdowns, aka doing things about, but that don't involve administering medication or vaccines, okay? Because we didn't have those at the time. And a whole bunch of, this was an extremely influential paper, and politicians read this report and they were like, oh my goodness, we probably should do lockdowns. How many people's lives would be saved? And then they published the code, and all these sorts of people are like, there's a ton of problems with this code. It is totally unreliable. It's a buggy mess. Okay. And as a scientist, you don't want people to say that about your code. You want to write code that's better than that. And I'm not trying to say we shouldn't have implemented lockdowns when New York City morgues were out of capacity, but ideally our policy decisions shouldn't be based on code. That's a buggy mess. We need to learn how to write better software. In my own field is molecular simulations. So we will put together a simulation box, we'll populate it with a bunch of molecules, they calculate how they interact and predict what properties that they have. People use this to do protein folding, study adsorption of pollutants onto porous materials, design catalysts. Okay, so lots of important applications in chemical and biochemical engineering. There was this popular science article called The War Over Supercooled Water, which detailed this debate in the literature in my field. If you have liquid water that goes below the freezing point, so let's say negative 30 degrees Celsius, does it have this curious little thermodynamic feature called a liquid-liquid critical point? And we had 2 groups of people who were saying, we should get exactly the same answer to this question, but we have completely different answers. No, there's not a critical point. Yes, there is. The answer is, yes, there is. And it's because the no side had a problem in their code. They had a complicated simulation, and one of these steps was scientifically invalid. It violated this principle of statistical mechanics that should have been satisfied, and they got the wrong results. This took 7 years to sort out, and in the aftermath of this work, a lot of people in my molecular simulation community have come up with approaches to make this better. Okay, say, let's write our software in ways that's transparent, reproducible, usable by others, make it extensible. If you publish your code and share it, then other people can help you find bugs if you might have introduced bugs without knowing it. The Molecular Sciences Software Institute, they are a really great resource for teaching scientific computing, teaching software carpentry to people doing scientific computing. So you can be a little bit more like a computer scientist and write better code. You're not a computer scientist. You're your expertise is in your domain of physical science or engineering, okay? But you're going to learn better software development practices. And there's people developing frameworks. Can we unify many different kinds of codes, have them run the same systems, compare their results, and evaluate their physical validity using automated testing? Sometimes the NIST, so this is the National Institute of Standards and Technology, they will develop these standards. So if you write code, you will run it under the conditions they have reference data for, and you check that. Okay. Today, I'm suggesting how we might take these approaches even further. Can we make code? How could we make code that's free of bugs, that's provably free of bugs? And what I'm doing is I'm drawing tools and inspiration from the formal methods community of mathematics. And they've been doing a lot of great work in the computer science space, in semiconductor industry, doing stuff on chip and stuff, but only recently have these tools emerged where I think it's going to be appropriate and beneficial to bring them into scientific computing. So let me be more specific about what I mean when I say bug-free. The first thing to talk about is what kinds of errors might we encounter? And the first error I want to bring up is a syntax error. And you've all encountered this if you don't close parentheses, right? Your code that you're writing, usually the code editor, whether this is Jupyter Notebook or if you're editing the code in a IDE like like Spider or VS Code or something. Okay, the editor will say, you have a problem, you didn't close your parentheses. So you fix it right away. Alternatively, we have runtime errors. So this means you typed up the code. The editor doesn't say there's any problems. You compile the code. The compiler doesn't see any problems, and then it runs the code. And now you get an error message. So if you try to access an element in the list that doesn't exist, this is going to be a runtime error. Now, runtime errors are really helpful because usually the program is going to tell you, go and find the error at line 150 or something like that. Then you can go and track it down. But they're really frustrating because you thought the code was ready, right? You shipped it. And sometimes these won't show up every single time you run the code. Maybe you posted it, you're collaborating with other people. Lots of people are supposed to use this software. And someone ran it under conditions you weren't expecting them to run it, and then it gave an error. So then you have to go back and fix the code. Semantic errors are the worst. So if you miss a minus sign, or maybe you transpose the indices of a tensor that's square. I mean, sometimes you'll get errors in runtime, but these kinds of errors require you to have a human inspect the code. Everything ran, the output of the code happened, and now it is wrong. So if you thought it was supposed to go up and it's going down, after you plot your results, well, now you know there's a problem. You observed some anomalous behavior. People recommend test-driven development to catch these things. If you haven't heard of that phrase before, unit testing, test-driven development, we're going to circle back to that in the second half of this course. This isn't something scientists and engineers typically learn about, but it is something you should learn about if you're doing any kind of software development. What we're proposing is an approach to move all of these kinds of errors and catch them at the editor stage. This means we're going to ship code that is free of syntax, runtime, and semantic errors. Is runtime also called a logic error? Good question. Is runtime also called a logic error? Not necessarily. I would say not necessarily, because I'm just going to simply categorize it as a runtime error. Logic errors could be more semantic in nature. The reason I sort of hesitate is we do use logic to prove that a program won't have any runtime errors. So that's kind of a curious thing. Like if you're having a runtime error, that means you messed up the logic somewhere. There was some kind of scenario that you didn't account for in advance. But what we typically think of as logic errors, I would say, is more going to be on the semantic side. All right. And there's one more category of errors, and that's going to be floating point and round-off errors. So if I have a really, really large number, okay, maybe 10 digits, okay, and then I subtract a really small number from it, 1 digit. So I have 10 million minus 1, and I have a bunch of digits on the 1, and now I cut off a bunch of the decimals after the 1 because it just doesn't fit in the floating point precision of this. So one of the software packages I worked a lot with, you might run into these errors, and way they would check it is they would say, like, after you run your whole calculation, check the starting point and the accumulated changes as you added and subtracted tons and tons of numbers from each other, and just check to make sure that the difference at the end of the simulation versus the beginning didn't really blow up into a big thing. We are not proposing to deal with those in Lean. Some people in the formal methods community aiming to work out ways to guarantee bounds on floating point roundoff error. That's not what we're focused on. For Lean, is it the editor or the compiler that gives the guarantee? I would say the compiler is that technically gives the guarantee. But when we access Lean through a good editor like the VS Code, then we actually get feedback in real time as we write the code. So I guess your experience of Lean, of writing code in Lean, is that you will be finding it as you're writing it in the editor. Okay. So here's a vision for bug-free scientific computing, and this is a neat paper for you to check out. This is where a lot of this vision, I think, comes from for me, is this 2017 paper, Developing Bug-Free Machine Learning Systems with Formal Mathematics. I should add, I'll be sharing all these slides afterwards, so you don't need to frantically jot down any content on here if you want to catch references or anything like that later. The standard method is you write a program, you run a test on the program, and you see if the test passes. If the test fails, then you go back and you fix your program, you fix the tests, etc., until you have code that passes tested. And this is what test-driven development essentially means. This is really a great way to write code that involves hundreds of collaborators and gets really huge. Like Google will have every time they ship a new piece of code, they will run it on hundreds and thousands of tests that people have written before. And if test 337 suddenly breaks, well, now you'll know to go and fix that so that your new addition to the code isn't breaking things. But ultimately, this only guarantees that code is passing the test that you write, code that passes the test that you've defined. And there's a different way that this can be done, and the idea is to verify code mathematically. Here you're going to specify at a high level what the code should do. Specify it with, technically it is going to be a step specifying this as a theorem statement about your program. Then you write your program, and you try to prove your theorem statement about your program. And if you're unsuccessful in writing your proof, then you'll say, oh, well, I made a mistake as I was writing my program. Or maybe I didn't specify my theorem correctly. But you'll work on this until you have all of the theorems that you aimed to prove being proven. Now you have a code with correct math, and this provides a stronger guarantee than simply test-driven development. So, for example, consider mass on a spring. We have the force is going to be negative kx. The energy is k over 2x squared. And we would say, the force and the energy have this derivative relationship. Now, if I was going to define these as functions in Python, I could say force of kx will return negative kx. Energy is xk and return k over 2x squared. So I can define a test. And if I pass in 5, 5 into my force and I get negative 25, I'll say pass or fail. And this can be helpful. And if this was one small part of a very large program and somebody messed up part of the code that was supposed to be passing this test, then running this test along with all the other ones would flag it as a problem. In Lean, we can also define a function for force and energy. And in this case, so the thing about Python is it tends to sort of figure out on the fly what your types are. You don't have to define the types of your variables, and we'll talk a lot more about types later. But in short, we're defining k and x to be the real numbers. And so what are real numbers? They are all the numbers 0, 1, 2, 3, but they also include fractions, and they also include irrational numbers like square root of 2, pi, and so forth. And I'm going to say my force is going to be output as a real number, and it's negative k times x. I could define my energy this way. And in Lean, you have this object. It's called a theorem object. And this is something you can define saying the force is the derivative of the energy. This is just the name of the theorem. And I'm going to go and write out in mathematical language that for all values of x, for all, that's what this upside down A symbol means. It means for all values of x real numbers, the derivative of energy with respect to x is equal to negative force. Okay, that's essentially how we'll read it. And we'll get into how you can actually parse and read Lean code later. But that's what this is going to prove. It is going to prove that this rather complex math description relating these two functions holds. And it doesn't just hold for one value of x, one value of k, but this holds for every single value of x. So the next topic is to really lay the groundwork. We need a few different pillars. And the first one is to realize that derivations in science and engineering are math proofs. So I'm going to bring a little background for my area. Adsorption is this thing in chemistry, chemical engineering, where we have molecules from a gas and liquid stick onto a surface or onto a solid material. And this is in your Brita water filter, catalytic converter. People use these in separating oxygen from nitrogen. So you start with air and you want to either make maybe medical grade oxygen, or you maybe want to make liquid nitrogen or something like that. So you need to do a purification. Adsorption is relevant in all of these cases. And people have all these little theories about adsorption because you go and collect data as the pressure changes, what is the loading of the molecules. And for a long time, people were like, how do we understand? I made this material, I measured its absorption behavior, I fit some equation to it, but how do we understand what is happening between the molecules of the gas, the surface? And we need theories to describe this. And I want you to think about this challenge. How can I get a theory to come to, how can I get a computer to understand theory? Here is a very important theory of adsorption. This is BET. This has been cited like 50,000 times. It was published in 1938. And if you would pass this PDF into an AI system and you asked it, just read this paper, tell me what's going on, it requires complex cognitive thought. Even if it's able to parse out what every character, how that maps to a mathematical symbol or a word or something like that. Broadly speaking, what BET theory says is I'm going to have potentially an infinite number of layers of molecules absorbing on this material. We have this surface area of the material. We have the adsorption coming on, the desorption coming off. And this all converges to get this expression in the end. And then we, as engineers, will take this expression and get some data and fit the unknown parameters to this. Well, when they were deriving this theory, these were the kinds of things that they were doing. Notice that they were defining a model. We shall let S0, S1, S2, and so forth represent the surface area that's covered by all these layers of adsorbed molecules. They express things in mathematics. This is an equality. We have multiplications, negative, division. All these things are mathematical terms. Variables are specified. P is pressure. It's not just some character in my math equation. It corresponds to something in reality, pressure. E is a heat of adsorption. We also need to make assumptions. So here's a bunch of assumptions that are being made in this particular theory. Then we have deriving new terms. So you set up all of these things, and then you say, it follows that. If you've ever read a scientific theory paper, they usually set up things, and then they say, and now I'm going to do math and derive new terms. And there's also an important thing that this doesn't just exist in isolation. We relate these theories to other theories. There's another theory. This theory was published about 20 years earlier, and it's a generalization of this 20-year later paper is generalizing Langmuir's theory to multi-molecular adsorption. Langmuir only had one molecule adsorbing in a layer. They said, we've just figured out how to generalize it. And so what we're doing is trying to make derivations in science and engineering into formal computer checkable proofs. And we're going to make these executable. We're going to turn the informal description of derivation into a formal derivation in Lean. And what that means is we need to turn something that's, we need to turn these derivations into math proofs. And this, I think, is an important insight, an important perspective you can have. You can think of any derivation, really, in science as a math proof. So consider this one. This is one of my favorite papers. I've really scrutinized it a lot over my career. And you can sort of boil down the main elements of this paper into 5 premises. Okay, I have 5 things that I just sort of assume. I assume a site balance, absorption rate model, desorption rate model, equilibrium, and mass balance. And then I say these 5 premises imply my conjecture. So now this is math language. This overall thing would be a proposition to say that premises imply some conjecture. And I would say that a theorem is stating that a proposition is true. And that then a proof is going to be doing the derivation. I would use some algebra. Like, you can kind of look at this, and if you've ever done a lot of algebra, you can see, okay, maybe I would rearrange some of these things. I would do substitution. I would cancel out terms until I eventually get Q is equal to the stuff on the right-hand side. So you can do this over and over again, right? Like, if you think of the things you've read and done in your science classes, then you work through these derivations all the time. And if we conceive them as math proofs, that enables us to put them into Lean. So the next big thing that we need to get into our perspective is, what does it mean to do formal mathematics with computers? So that had around for hundreds, thousands of years. People write these rather informally, and it's readable by humans, but these might exclude information. They might have mistakes. They require humans to proofread them. Nonetheless, they're relatively easy to write. Formal proofs are harder. They're more challenging to write because you need to follow a strict computer language syntax. But the benefit of that is the machine can read and execute these proofs. They can't miss any assumptions or steps, and you get rigorous verification by the computer. And one of the really beautiful things that comes out of this is you can have massive libraries of proofs with hundreds of thousands of things that have been checked by the computer. And I would say, so Mohammed is asking, so the purpose is turning observations and scientific proofs into mathematical equations that can be understood by a computer. Yes, I would say, with an asterisk around observations. Connecting this to observations is something we're going to talk about tomorrow more. That bringing this into a connection with the real world is harder than just formalizing the theories themselves into mathematics. So the other aspect of formal proofs is thinking about axioms. Alfred North Whitehead and Bertrand Russell wrote Principia Mathematica 100 years ago now. And their goal for this was, can I express mathematics in symbolic logic and minimize the number of axioms? So an axiom is a most basic assumption and inference rules. So I could say, like, can I describe all of mathematics using a very, very small bit of stuff? And they did a lot of work. They wrote hundreds and hundreds of pages. And in volume 2 of this, after a 300-page volume 1, they get to page 86, and they say, and therefore 1 plus 1 is equal to 2. And this above proposition is occasionally useful, they say. It is used at least 3 times and then provide references in a few more places later on in their book. So later, people in math have come up with other ways to do that. And so Zermelo-Fraenkel set theory is one of the more well-known ones. And version I like about this is you can actually just list all the assumptions, and you can look these up on Wikipedia, for example. And you just write down these 10 assumptions, and you can, from these, derive almost any mathematical expression and proof. And they have things like 2 sets are equal if they have the same elements. If x and y are sets, then there exists a set which contains x and y as elements. There exists a set having infinitely many members, and so forth. So you just combine these 10 different fundamental axioms and start defining new things and proving stuff about them, and you can build up mathematics. So what does this look like? One of my math professor colleagues at UMBC wrote this popular science book about how to build up mathematics using axioms, and he's talking about how to count with sets. So we define an empty set as 0. We say the empty set encloses nothing, and if you define a set that encloses the empty set, then we define this to be equal to 1. And we define the empty set that includes, we define the set that includes both 0 and 1 to be 2. And if you put in some set theory syntax in all of this, we get a definition of 3 and so forth, and we can formally define what counting is. This is the succession operator. I apply succession to 0, I get 1. I apply succession to 1, I get 2. And I can go and get the natural numbers if I have recursion and succession and the empty set. That's all I need. And I have all of the counting numbers. This is 0, 1, 2, 3, 4, 5. It goes off to infinity. I just need to define 0 and use recursion along with succession for this. And I can define addition. But I'm not going to simply define addition as a standalone rule. I'm going to define it using the axioms and rules of mathematics. So what we do is we start with succession. We've already defined succession. We have properties about how succession works, and I'm going to then use succession and recursion, the empty set 0, and I'm going to define what addition means. Then I go and define multiplication. Multiplication is very similar. I recursively apply addition, and now I get multiplication. You can define an inverse operation. Now we have subtraction. Now we have division. Okay, you can go from multiplication up to powers. You can go from the inverse of powers would be the root, right? You can start thinking of those things. And so that's how we actually can do this. But in practice, there's this big chasm, this gulf between the mathematicians who do research and devote their life's work to study the foundations of mathematics. That would be this formal proof, okay, and mathematicians doing new math, traditional proof. And that's how Thomas Hales, an expert in automated reasoning, did in this great review on formal proof. We have this huge number of arrows here. How do you bridge that? There's people working on the foundations of math. There's people working on new theorems based on discoveries in the last decade. And in 2008, there was a wide gulf between these. But that gulf has shrunk considerably since then, and it keeps growing smaller and smaller. People are now doing modern mathematics with theorem provers, tying it all the way down to the axioms of mathematics. And that's possible because we have new tools now. So when we first had computers, mathematicians started using them to check proofs in logic and mathematics. And people would, so the sum of even numbers is even. That was back in 1954, some very, very early computers. And a very landmark paper in theorem proving is the 4-color theorem. So this is a famous problem. You have a map of polygons spread out on some surface, and you're going to ask how many colors do I need to color this so I don't have two adjacent regions sharing the same color? And they successfully used a computer to prove this, but it took over 400 pages. They used a computer to do this. So like, that's not a typical theorem. Like before this, every single math paper had been written as a pencil and paper kind of style proof, typed up. Mathematicians read it. This is 400 pages. It's brute force. It's like, and people, this generated a lot of controversy. How do we know the computer did it right? I can't read, I can't easily read those 400 pages by myself. Is the proof by computer meaningful or interesting? In the 1980s, people improved technology and they advanced in software. So some other theorem provers, especially Hall and Cock, higher order logic, and so Cock is named after the the French person who created that. Type theory started becoming, so I've told you about Zermelo-Fraenkel set theory. Type theory is an alternative way to lay the foundations of mathematics, and that's a lot more popular now among theorem provers. And this opened up more possibilities for more complex proofs that can be written in axiomatic math. And interestingly, in 2004, Gonthier took what had been a proof just written in some programming language that was supposed to be checking the four-color theorem, instead writing it in a theorem prover where every single aspect of the mathematics of the four-color theorem was tied all the way back down to the axioms of mathematics. So after this was done, then there really wasn't much more doubt in this proof anymore and in this paper, because now we really have confidence that these people didn't introduce a bug into their code that then suddenly missed an edge case or something like that, and said it was, and came up with the wrong conclusion about the proof. That same story happened with the Kepler conjecture. The Kepler conjecture says, is the hexagonal close path, the face-centered cubic version of that, is that going to be the most efficient way to pack spheres in three-dimensional space? That was rigorously proved using a brute force approach in 1998, and then a similar approach, but tying it all the way back down to the axioms in 2017. But each of these sort of, and I'll leave it at that. So what's happening differently now, though, is consider this little story. In 2012, Peter Scholes posted on arXiv this paper about perfectoid spaces, saying, I invented a new math idea called perfectoid spaces, and he was awarded the Fields Medal in 2018, and that caught the attention of these people who were working with Lean, this new theorem prover. And they said, hey, what if we tried to formalize perfectoid spaces? And so the three authors in the Lean community, you can go find them now, still developing Lean, they said, hey, let's do this, and they successfully did that. So between 2018, when they said, let's try to do this, in 2019, when they successfully did that, this bridge is shrinking a lot. So what did that take? Quantum Magazine wrote up a great article on this, and they said, to define a perfectoid space, the three mathematicians had to combine more than 3,000 definitions of other math objects and 30,000 connections between them. These definitions sprawled across many areas of math, from algebra to topology to geometry. And so this was a visualization of all these little things. So these are little definitions of stuff across all of mathematics, and they had to have a single math library that brought them all together. Another neat thing is in 2022, I like this one because a big math problem got a new answer. And so this was an informal proof. They wrote it up, they submitted it, they posted it on the arXiv. It went into peer review at a math journal. And then in a few months, the author of the new proof teamed up with an expert in Lean, and they verified the correctness of the proof in Lean. And the advisor of the Lean expert is saying, I'm very excited that they've done this. This is probably the first time a serious contemporary result in mainstream mathematics doesn't have to be checked by a referee, doesn't need to go peer review because the computer has been checked formally. Might be a sign of things to come. That it was still waiting. You know, it was still out for review, and the mathematicians were reading it, trying to see if that was going to be the case. People have since been talking a lot more about, like, what is the purpose of writing and publishing code? Writing and publishing math papers if in the future computers will be checking these for us. But math is changing, and these theorem-proving tools are a big part of that. So that gives you an idea of what it means to formalize math. Let's talk now about Lean 4 and mathlib, the theorem-proving system we are focused on. So Lean was developed in starting in the 2010s at Microsoft, where Leonardo de Mura and his team at Microsoft developed the Lean program. And the idea is, the reason it's called Lean is because the kernel of this, the core of Lean, only has 6,000 lines of code. And now, just like I was describing before with set theory, you start with these 6,000 lines of code and you write things outside of that trusted kernel, and then you use that kernel to prove that the stuff you wrote outside of it is correct. So I just checked yesterday. Now there's more than 150,000 theorems, more than 1.5 million lines of verified math proofs, where stuff about multiplication is tied to stuff about addition, and everything is interconnected together. Lean has these tactics to facilitate proof automation. One of the challenges of the old tools is it'd be really tedious to dot all of the I's and cross all of the T's to make everything exactly rigorous with the computer. If you have automation, then you can employ these tactics, and you can very efficiently put all of the minute details under the hood, so to speak, so that you just see the more human interpretable high-level stuff on your screen as your code. A really neat thing about Lean 4, which is the latest version of the code, is that you can compile it to C code. And so as scientific computing people, okay, take note of this. This hasn't really been rigorously tested. Like if you built a scientific computing app in Lean and then compiled it to see how efficient is it going to be, we're working on that test ourselves. But at least in the possibility that you'd be able to potentially run these on the supercomputers that we do all of our scientific computing on. And the vision for the math library of Lean is to digitize mathematics. And that's going to make mathematics better, make it more rigorous, make it more searchable, make it more interconnected, unified, things like that. So Lean's math library is called mathlib. And this question is, what do we need to get the real numbers? The real numbers are numbers like these. And all you need to do in your Lean code is write import mathlib.data.real.basic. You just need to find the import, essentially. Now you're going to draw on the Lean math library. So what does this look like? I'm going to quickly show you a visualization of the math library. Now, a caveat, this is a Lean 3 visualization from the old math library from a couple of years ago. I just never got around to updating this graph, but the general idea is the same. If you zoom in and look at the top of this, you're going to see things like logic.basic. Basic logic, okay? We're going to start with basic logic, and then every one of these little loops is going to be a file in the Lean and or mathlib ecosystem there. Everything is interconnected together. And we go down and down and down and down. And at the very bottom, we get the real numbers. And we can construct the real numbers by using Cauchy sequences. So don't worry about what that is if you've never heard of those before, but it's a rigorous thing that comes from a real analysis perspective. That typically is sort of like a proofs class number 2 that you would take if you were doing a math major. But that's how you can then rigorously define the set of numbers that includes every single real number, including the irrational numbers like pi, square root of 2, and so forth. Let's consider another example. Stirling's approximation. We use this in statistical mechanics a lot. I have n factorial, and I'm taking the natural log of it. It's a massive number. And if n is the Avogadro's number, 6 times 10 to the 23rd, okay, that's massive. I don't want to take factorial of that, okay? But I can take that number and I can reduce it a lot. And where is Stirling's approximation to mathlib? I can import mathlib.analysis.specialfunctions.stirling. And what I now have at my disposal is a theorem statement about Stirling, and this is what the dependency graph is. The real numbers, they're about a third of the way down here. And I needed to go and build all of these other things in order to prove that is the case. The Stirling's approximation proof, if you want a very quick 30-second rundown of what it entails, we have defining the natural log as a sum and approximating the sum with an integral. So we need calculus integration. We use the trapezoid rule. So they have the error in this formula comes from the Euler-Maclaurin formula. So you need to define the Euler-Maclaurin formula and prove its properties. You need to define the Bernoulli number and prove where that comes from. You need to take a limit as n goes to infinity. You use this summation from k equals 2 to m of all this stuff, and finally it all breaks down into the thing we're looking at. So this is all of this complex math stuff. You can define that and you can prove it rigorously in Lean. And scientists and engineers don't need to know all of these steps. I don't need to know how I got here. I can just import it and now I can use it. As long as I know how to apply a theorem to something that I'm working with, and I'm able to shape the thing I'm working with into a form that is able to admit the theorem that I've imported from the library. Okay. All right, I'm going to jump back in. Okay, so before I get to the next part, I've got a question from Vic. Computationally intensive math, like finite element analysis, requires tremendous computational churn. Has there been any work in that direction? Given error propagation can be hard to trace back in finite element analysis systems. How would all these be addressed in the editor itself? As stated in the first slide. I'm going to jump back to that slide. This would mostly be in floating point errors. And we are not trying to address things, what we're talking about here is mainly trying to deal with did you define the logic of the finite element analysis program correctly in the first place? So when you turned the calculus into finite elements, you didn't screw something up there, okay? After you start giving it numbers that have finite precision, those old proofs don't hold anymore. And they hold for the logic, assuming you had infinite amount of precision, essentially. Your question, has there been any work in that direction? Yes, there has. And I'd have to hunt to find particular references since I don't follow those too closely, but people in the finite element community are very interested in that, and people have been doing stuff in that area. We're not particularly focusing on that, but Lean could be used to do that if people built the tools in Lean for that. Good question. All right, I'm going to now show you a little bit more of what Lean. Actually, no, I'm going to save this for later. And we're going to move on to, actually, no, it's time to do a very simple proof in Lean. So you have this proof in the link I sent, and I'm going to pull it over my VS Code so you can see what this looks like and give you a feel for what it's like to write code in Lean. So we have a theorem statement. I'm defining all of these numbers as real numbers, and it's curious. You see, I put my cursor over one of these, and the cursor is going to say R is of type real number. I then define assumptions. So I have 4 assumptions, H1, H2, H3, H4, and then I have a colon, and I give my conjecture. And, oh, I didn't actually explain this slide. Okay, what we're trying to do is we're going to prove that an ideal gas follows Boyle's law. So this is a simple little example from thermodynamics. PV equals NOT. If T1 is equal to T2 and 1 equals N2, then we get P1 V1 equals P2 V2. Okay. So I define my theorem statement, and now I need to prove it. So what does it mean to work in the Lean's editor? Here I've opened it up in VS Code. On the right-hand side, you see the Lean info view. If I put my cursor right here, after the by, you will see I have tactic state. And there's a goal. I need to prove P1 times V1 equals P2 times V2. And I have all of these variables, and I have all of these propositions, these equations, these assumptions in my premises that need to imply this conjecture. Now I have a tactic. RW is rewrite. It tries to do substitution, essentially, is one way to think of how this works. So I'm going to rewrite my H3 at H1, and if I put my cursor after this, now I have H1 has changed T1 into T2. I'm going to go back so you can see. T1 is started. Now I put it after it changed it in T2. And maybe on your screen is highlighting the T2 to show where the change happened. Easier to see on my screen maybe than yours. Okay. Next we do rewrite H4 at H1. Now you can see the N1 has changed to an N2. I can do a rewrite. Instead of making the substitution on the right-hand side of the equation, I'll make the substitution on the left-hand side of the equation. And I'm getting that from the H2. I'm getting the left-hand side of this. So now I will have P1 V1 times equals P2 times V2. And now I have a goal. P1 times V1 equals P2 times V2. This is exactly the same as one of my premises, so I can conclude it. I can prove it by saying exact H1, and now I get no goals showing up in my system. Isn't that great? No goals. I'm satisfied that I no longer am trying to prove anything. Some proofs you'll end up will split. You might start with one goal, and then all along the way, you'll break it into many different goals, and then you need to close each one of them one by one until you've covered all of your edge cases, for example. Now, this is a whole bunch of stuff, and people often ask, so does the computer just give this to you? No. You have to write these steps yourself. That's why we teach you how to do theorem proving. We'll talk briefly, and we'll talk more later about using AI to autocomplete code. So you can have AI sort of fill these steps in for you. They're getting better, essentially, but still it's really good to learn how to do this yourself. You also don't need to take up so much space. Here I have a short version of this where I just set up this whole goal and I say rewrite. I can combine all of them together. H1, H2, H3, H4. This one closes the goal all in one line. So you can't see as much of what's happening here, but it's proving it nonetheless. And this is a shorter code. So I usually show this first example to walk you through step by step of what it's doing. And then the second example is going to be something that would be more production type proof that you would say you would want to make your use fewer proof steps, consolidate things, make them more concise, more readable. There's multiple ways to prove the same thing. So that's what lean looks like. Now I'm going to give you a few examples of case studies. And great comment from Martin Dvorak, who gives a suggestion of how to see the intermediate states I'll just show that real quick. Yep, in this one, I can actually put my cursor after each comma in this compound rewrite block to see the step-by-step changes that are happening as well. Thank you. Okay, back to... so can lean be used to write new proofs, or can it only be used to verify existing proofs? Good question. You need to know how to do it yourself. Often what people will say, I'm trying to prove this thing. How do I do it in lean? And if you're a beginner, often one of the first things to ask yourself is, do I know how to do it pencil and paper? Do I know logically how I should be approaching this? You kind of need that as a prerequisite to decide how you're going to go about doing the proof. And the same thing goes with scientific derivations. You might find something written up in a physics paper and they don't actually have all of the details in there, and you need to turn on some extra mathematical chops, essentially, to go and figure out how to make it more mathematical than it was in order to define it precisely inside of the theorem proving system. That said, there are AI tools. I think they're rapidly improving. And as these become broadly available and easier to use, I think then scientists and engineers might become more responsible for, can I define my example correctly? Can I state my theorems correctly so that it corresponds to the science that I want it to correspond to? And then can I autocomplete the proof? If I can't autocomplete the proof, maybe the AI system failed, maybe I didn't write it correctly. Okay, but if the AI system does successfully prove it, then I don't need to worry so much about exactly what it's doing. I can trust that lean has its stuff together correctly. All right, so let's talk about some case studies. So a little over 2 years ago, I started getting interested in lean, and I introduced myself. The lean community asked, do you hope to explain chemistry to lean? And in short, yes. Yes, we do. And late last year, early this year, we published this work in the Digital Discovery, where we figured out how to formalize chemical physics. This was a journey. We ended up writing all of our proofs in Lean 3, which is the version that was current when we got started in this project. We're all learning Lean 4. You should not learn Lean 3. Lean 4 is the future and the only version that's supported now. Our paper, though, is written in Lean 3. It's how it goes. We're working on, at some point, we'll create a cleaned up version where everything is all Lean 4 and you can follow it more closely that way. But the main idea is the ideas. Can we formalize chemical physics in a theorem proving system? And we formalize some derivations. we do logical connections among gas laws, and we show how you can derive kinematic equations using calculus. And some of the things we learned from that, I was showing you the Langmuir paper. Well, we were writing the paper, and you have to write the paper in LaTeX, and so I had written out this thing, and we made a mistake, okay? We made a mistake in the LaTeX. This equation right here in the denominator, it was an S instead of an S0, and we didn't catch it. The peer reviewers didn't catch it, okay? Not after a couple rounds of peer review. It was a community member that we were sharing with and discussing the paper with. They found it and said, hey, by the way, should this be S0? Well, yes, it should be. If we had written the paper itself in lean and had all of our equations be lean objects, essentially, that were automatically turned into LaTeX expressions, then we wouldn't have made that kind of error. I also showed you proof number 1 of this in Boyle's law. Another thing that we did here was to show that you can expand this idea. This proof is not actually that useful. It's good for exercising, and it's good for learning how to do lean, and we're going to have a lot of theorems and examples that we solve like this, so we can learn how to use the tactics of lean. But essentially what all of this includes is these assumptions are self-contained inside of this theorem, and they don't touch anything else in the system. What we did here was we started defining using definitions and structures, and we're going to get to those in a few weeks, so we can reuse ideas and multiple proofs. That's really what we're trying to go at. I mean, that's how mathlib is built. Mathlib has one mathematical idea that connects to hundreds and thousands of others. We want scientific ideas to be defined like this and then connect them to hundreds and thousands of others. So we built a little system about gas thermodynamics to say that I could have all sorts of these different theorems. I have 9 of them listed here. We did even more. All of those things are proven to be true about this system that we're doing. And we have things like an ideal gas is a specific instance of a thermodynamic system. I could extend a thermodynamic system to a different thing than an ideal gas. It could be a van der Waals fluid. It could be other types of things, and prove things about that. And the fanciest proof that we did in this paper is formalizing BET adsorption theory. And so the 6 main premises ended up looking like this, and we also needed to go and require constants to be greater than 0. Like pressure is going to be positive, for example. Like negative pressure exists, but it's not super common in regular thermodynamics. Okay, and one of our stories for this was really helpful. We didn't have to use this kind of using this geometric series relationship. Summing I from 1 to infinity of x to the I is equal to x over 1 minus x. So we didn't, so the theory in the paper, they invoked this theorem and another one like it. But they didn't say the conditions that are required to be satisfied. X must be greater than 0 and less than 1 in order for this to be satisfied. And later people, after the very first derivation of this, later people re-deriving this in their own papers were saying, by the way, X is constrained to be these things. They didn't mention that in the original paper, but these extra conditions are made explicit in lean. I'm not allowed to apply the theorem that defines this transformation until I also have the proof or the statement that X is between 0 and 1. And along the way, we also find a minor logical correction to one step of the author's reasoning of this. Has to do with the limits. As limit goes to, pressure goes to the saturation pressure, the loading goes to infinity. Lean didn't allow us to use limits the way that the authors of the paper were saying they would be used. We had to reformulate the way they did their reasoning in order to make it rigorous and provable by lean. All of this didn't change the high-level view, or the high-level contributions of this paper, but it did make the overall derivation more rigorous and make it computable, made it executable. All right. I'm going to wrap this section up and address the rest of the questions during the intermission. Okay, so another case study is in programming. And we haven't published this work yet, so you're getting a preview of what we've been working on. And this idea is bug-free computing. Can we actually build executable code for this? So this one comes back to this BET theory that I was talking about. And people use this nowadays. People will go and collect loading data. And so you will go and get loading data on these points as a function of pressure. And Q is loading, P is pressure. You can linearize it, just rearrange this equation and then do linear regression to get the constants in this that are most important, the surface area and the interaction constant, C. And the funny thing about this paper is they were saying, well, you're going to find the surface area of this unknown material by doing BET analysis. What answer should you get? And what they did was they did a round robin study, which means they collected the same data sets and they went and they said, so here's more than a dozen different data sets, X and Y columns of data, Q versus P, basically, and said, do BET analysis and tell me the surface area. And they sent this task to, I forget now, 30 labs, 50 labs, something like that. And all these researchers then did their analysis, they sent their results back, and then they consolidated their results. And sometimes the area measurement is off by four factors. It's wild. And so where does this come from? Well, the high-level steps of BET analysis is you filter the data to focus on the BET regime. And this is where the biggest part of the error comes in, is because some people weren't, they were filtering in different ways. After you do this, you linearize the data, you perform linear regression, you get your fitted coefficients. Some of them don't linearize it, they perform nonlinear regression. So that's another way of getting slightly different answers to this. And the multitude of results caused the organization to say, like, let's say, here's a Python code where we have like over 100 authors have all taken a look at this and said, we believe this, we think this is a good standard to move forward. Well, what we can do in Lean is we can start writing proofs about this idea. I can go and derive BET theory. And can I conclude that this equation follows from my body of assumptions about the theory? If I do that, I am very confident that I don't have a typo in here. Like, is this supposed to be a minus or a plus? Right? If I do linearization, if I turn that into a linear equation, did I make a mistake in that? You know, this is a semantic kind of error that people might introduce their code that you're never going to get flagged by Python, but we would be able to catch by trying to prove this to be true in Lean. We can also do purely math things. Can I prove that linear regression minimizes the least squares error? This is a property of that should be true of linear regression in general. Anytime you do linear regression, it should do this. Can I prove that? And that our code that implements linear regression is actually satisfying this high-level property about the regression. And then finally, we could have a proof that the output, the fitted coefficients that come from my software, corresponds to the meaningful parameters that ties all the way back into the body of assumptions about my theory. And this is all stuff that we can do in Lean. And Lean is going to rigorously tie every single little one of these things together by having proofs about all of these things, using the same objects, and all of that. So there's another complication, and we're going to talk about this a lot and do exercises of this in the second unit around bridging this world of floating point number calculations and real numbers. So we can write proofs in real numbers. We can't write proofs, the same proofs about floating point numbers. If A and B are floating points, I cannot say A plus B minus B is equal to A. A plus B minus B is equal to A is not true for floating point numbers because we could get round off error if A and B are big numbers, are very different sizes. And that means we basically can't prove a lot of stuff with floating point numbers, but we can prove a lot of stuff for real numbers. And all of this stuff would be proofs about real numbers. And we use polymorphic functions. And so that's a rather advanced typing technique. But we can use this to sort of bridge the realm of computing and the realm of proofs. And that's what this whole course is about, is how do we bridge that? So we need to learn how to write the program on the top and how to write the proofs on the bottom and how to bridge them. And that's what this course is about. So finally, before we take a break, I'm going to give a little bit of outlook on this. And we're also working on Lean for molecular dynamics, formally verified molecular dynamics. And here we are going to, can I define molecular dynamics as symbolic formulas, Newton's equations of motion, force field equations, and then approximate these symbolic formulas as executable code. This is a lot. Okay, so that's the core part of what molecular dynamics involves. In Lean, I can go and write math specifications about these symbolic formulas. And can I prove all of these advanced properties about this? I can also do bigger stuff. Formalization of statistical mechanics. Can I prove that some abstract idea like the NBE ensemble in statistical mechanics? Can I do a big derivation of all of that in statistical mechanics and then prove the ND code as modeling that? That'd be pretty cool. We also have execution specifications, and this is a lot of what Tomas Scriven is doing in Silene, where can I prove that the Verlet algorithm is valid for approximating the ODEs? And things like this. Can I ultimately, after all of this, have formal proofs that the execution that I'm writing is valid and it corresponds to these symbolic formulas that I'm trying to write as executable code? And then finally, could we compile it into C code and run it? And how efficient will this be? We'll find out. Will it compete? It doesn't necessarily, in my view, it doesn't necessarily need to compete with the highly optimized MD libraries that people have been building for decades. We're trying to do something new and creative, but if it could be 10% or 50% as fast as those, I'd be really excited. And one of the neat things we can do this is I could write some bit of code that's efficient, and then I could, but really hard to read and hard to understand. And then I could write some bit of code that's easy to read and easy to understand. And could I then prove that my efficient code does exactly the same thing as my easy to read code? If I can do that, then I can trust the efficient code and all versions of the code that I write to make it more efficient. If doing that invokes some kind of approximation or condition, could we have the checks and the conditions built in to say, looks like you're trying to run under numerical under conditions of the variables that aren't going to be valid for these things. That'd be kind of a dream for us to go after. Another thing that we need as scientists and engineers is more stuff in mathlib. We have 150,000 theorems, but it's not enough. The library keeps growing. We have some specific things. These are all from chapter 1 of Statistical Mechanics by Don McQuarrie. But that's the thing. You can define new math and you can add it if you have the ability to do that, if you go and learn that. Another thing that I've been learning is sometimes mathlib has stuff, but it's just not in a form that's easy for non-mathematicians to use. And partial derivatives is an example of this, where non-mathematicians, you learn partial derivatives in Calc 2 or Calc 3, and you learn them in a bit more of a hand-wavy sense than they're rigorously defined using a much more general Fréchet derivative that mathlib has. Mathlib is always going to, the people creating mathlib want to make the library compact and efficient, essentially. And so you're not going to keep us more general. You're not going to keep two versions of the same theorem if one of them is subsumed as a by a more general version of that. But sometimes the more general version is harder for us to understand. And so that's something that we can get some help from the mathematicians to help us translate the more advanced math concepts into language and into syntax that we can adopt and understand. There's just a lot of opportunities to do automation to make mathlib and lean and VS Code easier to use and easier to follow for beginners. And a big one of those is AI. So this is an old paper. I just didn't have time to update a brand new result from this week. There's a competition actually on using AI to solve theorems, and it just released its results. We had 29 out of 50 math Olympiad problems were solved, and these were a sort of a secret test set of these advanced math Olympiad problems that were solved by the best AI tool proposed this year. It will go up next year, and the aim is to build an AI that can auto-complete proofs. And you can also chat GPT to be a lean code assistant. You can try these kinds of things, and they don't do a lot of. I think they're more helpful for programming, but in general, this is a rare computer language. It's like not even top 50 in most popular programming languages, which means there's not a lot of training data in these general AI tools unless they're fine-tuned on lean. And that means you may not find it as helpful as you find it for writing Python code or things like that. These also there's a lot less room for error in this code, in this style of coding, than there is in writing Python code, for example, because it's going to flag errors a lot more often. You can paste the error messages back into ChatGPT to see if that's going to help you. But I would just say all of this is not a substitute. I want to emphasize, not a substitute for learning lean on your own. Okay, you need to actually learn the math if you can. You need to actually learn how to do the programming if you can, because that will help you. It will help you use these AI tools more effectively. It will help you solve problems that the AI tools can't solve. It will help you clean up code, make it work better, come up with creative ideas. All those things are important for you to do the human learning and not just the machine learning all the time. Okay. And so we have this vision. Could we build this scilib, a companion to mathlib, where we would have a database of formally verified science? I have a bunch of topics. This is all in chemical engineering, and we have thermodynamics, but maybe we would have libraries of physics. There's a group of people in physics in the Zulip lean community who have been doing things in particle physics now, and their work is really exciting. A lot of questions that we need to figure out. How will we define standards for this library, and what will make it useful? What style of proofs do we want to bring in? This scilib would depend on mathlib. We would just build it on top of what the mathematicians are going to build that's universally true for all of mathematics. And then we would have come up with a way of defining the semantics of science and interrelating all of these exotic fields that would be then have their rigorous derivations. Okay. And so now when you go back and look at the schedule, I hope you have a better idea on how and where we're going with all of this over the next few weeks, and excited for those who want to stick around and do that. I want to definitely thank my research group. And don't leave yet. Okay, don't leave yet. We're going to take an intermission, and then we're going to actually dig into practicing lean, okay, after we take a little music break. But I want to warn you. So definitely thank my research group for digging into these things and learning lean, going out on a limb on this exotic, unusual research direction. Definitely thanking the lean community, thanking those at Carnegie Mellon University and Microsoft at IBM who've been helping us, helping mentor my students and me in learning this tool, especially thanking the National Science Foundation and UMBC Startup Funds for providing funding for this work too. All right. And now I'm going to start some tunes and chat about all the questions. We're going to talk about syntax versus semantics next time, tomorrow, on the question of accuracy. Bottom up. Yes, you do need, okay, the other assumption is working knowledge of the theory to make a model. Yeah, you do need working knowledge of theory. And by the time you can make the model in Lean, you will know that theory way better than you did before. You need to know the math and the theory, because you can't go and define a theorem statement incorrectly. Lean isn't going to flag you to say, you've stated your theorem incorrectly, because you can state whatever you want. It is still on the scientist to do that. Now, if you state it incorrectly, usually that means you can't prove the stuff you wished to prove about it. So it will sort of guide you in that direction, but the proof steps are very much, it stops you in your tracks. Now, you said bottom up manner, and I bring up statistical mechanics because it is something where the actual field itself is built in a bottom-up manner. People build up statistical mechanics by defining the axioms of statistical mechanics. These people will say, these are the premises, these are the basic assumptions. And in my lecture notes, when I teach graduate statistical mechanics in the fall, these are called postulates of statistical mechanics. Now, not every field is like that, though. Thermodynamics, you might start in the middle of the theory. For example, if you're starting, and so there's a question of, and I talk about this in our paper, do we start in the middle or do we build them up from the bottom up? If you're starting at the bottom up, what you're trying to do is you're trying to formalize science itself. And this is also known as Hilbert's sixth problem. And it's been around for 100 years. A lot of people have tried to do it pencil and paper for a long time and made various amounts of progress defining the axioms of physics and then deriving from the axioms of physics everything we know. And it's made a little progress, but it's just a really, really hard problem because this is tied to observation and verification, and it's really a different kind of question than trying to formalize mathematics. A neat paper I saw talked about seeing physics not as a tree, so to speak, where you define at the root everything and then all of physics grows out of that, but instead as a collection of proofs. You have a whole bunch of little, I mean, I just came up with this analogy, a garden, if you would, where you have a whole bunch of different plants, and maybe they intertwine here and there, but we can sort of be starting in the middle on these things. And it should be very obvious by our paper and the work we've done, you totally can start in the middle. I'm not sure, though, if how viable it will be to build a massive database of formally verified science if we're starting in the middle. Maybe we'll figure out some clever ways to do that. And a question about main difference between Lean 3 and Lean 4. Lean 4 added the programming components. Lean 4 is what makes it possible to do the programming side. So right here, Lean 3 can do all of this kind of stuff in the green realm, but really wasn't built to be a programming language. So the stuff in the top, a lot harder to do in Lean 3. Lean 4 is actually designed to be a programming language. And so it has an intentional design to make input-output operations. So I have all this kind of stuff. Do I have input-output lists, arrays, indexing? All of this stuff just works a lot better in Lean 4 than it did in Lean 3. Lean 4 compiles to C. Lean 4 is a programming language itself. So that's another thing too. Okay. And oh no, you couldn't hear me at all with the music playing. I might have to record that part again for YouTube. Um, Great questions. Okay, but bottom line, the most important one is the slides will be shared, and we're going to get to how to stay connected in the next part of the thing after this intermission. And I do want to talk about Ruben's interesting question too. Theories that are approximations and macro behaviors of systems, thinking of like ideal gas laws. How does this notion of this is a theory that is a trend and not a law get coded into Lean? I can simply state I have a classical thermodynamic system, and it has pressure, temperature, number of molecules, and volume. And I can then simply state that a proposition, PV equals nRT, is true about this system. And now I have a proposition, PV equals nRT, that I can start doing stuff with. So you can jump into the middle like that, and it's a sense, I'm just talking about a trend, an empirical relationship. Now, I could do that, and I could also then say, let me do a lot harder job and define statistical mechanics and define a thermodynamic ensemble and say, so if I've defined my underlying system like this, I would propose my system to have these properties and then derive the ideal gas law from this. And what we would do is we would aim to connect the statistical mechanics to the macroscopic thing. So that I would say, I have finally landed on something that now says I bridge all these things. So I have the classical bridged together with the statistical perspective, the macroscopic bridged together with the microscopic. If approximation comes into the play, well, we're still working on that. There's a lot of different ways to try to do approximation formally. Limits are one. So like a lot of statistical mechanics, it's in the limit as the number of particles goes to be infinity. So you can take a limit and now you have a macroscopic system that's infinitely large, right? They're not limits in Lean either. They're called filters, a more rigorous way of doing limits too. But we're not actually covering limits in this class. We're actually skipping all the way to calculus proofs instead of doing sets and then topology, because just for the sake of time. But there's definite resources if you want to do things like that I can point you towards. There may be other ways of doing approximations, and we may find different things. The mathematicians, I guess big O notation is another one too. That we saw that one with Stirling's law, the order of the error with that. So it is possible to formulate those. I'm not sure. I don't know the details of how to do that one. I haven't actually taken a breath. I'm going to take a breath. Okay. All right. So if you're still with me, that means you want to stay connected with this course. So here's the instructions for that. Oh, by the way, these are people who registered. Hello. Thanks for joining. We had around 370 people registered for this before I took these statistics down. Let me try to see participants list again. We have 70 people who are sticking around. I saw I have 85 or so coming to the online session. And You're about a third undergrad students, about a third grad students, and about a third working outside of academia. Um, Only about 40% are in engineering or physical science. Those people still are the main audience for this. Okay, so I know a lot of people in computer science got excited when they saw this on Twitter and said, "Hey, I've always wanted to learn Lean. This should be pretty accessible to you too." But our main audience is scientists and engineers who also don't know very much about coding. Um, the mathematicians, you're welcome to come here too. Um, we love mathematicians. If you're in mathematics, there's a lot of other tools for you to learn from. Be sharing those, especially mechanics of proof, mathematics in Lean. So if you have a deeper mathematical background, you can probably go a lot faster if you get the textbook mathematics in Lean and go into that. Or if you do theorem proving in Lean, those types of things, like if you've already gotten a math degree or you're doing a PhD in mathematics, you can probably see content faster that way and go a lot deeper in that way too. And you need a lot more than we cover in this course to do a lot of the interesting proofs that are being worked on in math. And for the scientific computing community, absolutely, um, this is what we're all about. So, um, okay. And if this is your first logic course, welcome. That's 67% of you. Really happy to have you here. I've never formally taken a logic course either, so we'll see how it goes. This is my perspective as a scientist who's an amateur independent studier of logic and philosophy of how I think this should be taught. We will see how it all turns out. Um, and then some, so if you're brand new to coding, I'm going to say welcome. Stick around as best as you can, get help. I have a feeling it might be easier if you've done some coding before, but we'll see. We're going to do surveys at the end of this to see how people participating in this course felt about the content, use all of that feedback to make it better for next year. And then a lot of people haven't done Lean before, and that's what this is all about. So, yeah, I'd love to see the Venn diagram on this. I've just kind of copied the brunt statistics, but I think the contributed to a collaborative software engineering progress is going to be highly overlapping with computer science. I mean, look at those numbers, right? These weren't exclusive. You could pick multiple fields of study, and the scientific computing people often have done this type of thing too. But but if you're a freshman in computer science, then maybe you haven't done this yet. So I might have to pull together some other stuff. And I do have a question, a direct message from a student saying, I'm newly admitted, just finished high school. Do you think I can keep up with the course? If you have the time, you're welcome to stick around, okay? Um, but the prerequisite for this course is Calculus 2. So, people who are freshmen, if you did extra math in high school or you passed basic calculus, in general, I'm saying you should be able to follow along if you've passed Calc 2 before. You don't need real analysis. You don't need to have taken discrete math or logic before. Those things are often covered. We're covering the basics of logic here. But you should independently know some calculus. I would jump back, like, even if you've just done Lean, you should be able to do, I mean, excuse me, even if you've only done algebra, and maybe Calc 1, you should be decent with Introduction to Lean and Proofs, Equalities, Inequalities. I think you can do Proofs of Structure 1 and 2. But until you actually know the math of calculus, it's gonna be hard to work through the calculus-based proofs that we're doing here. All right. So that should be some things if you're thinking about this for yourself. whether you're listening to this recording or you're here online. And if it's been a while since you've done these kinds of maths, good luck. Just take your time on it. It's way better to have seen this and learned this the first time than for it to be brand new. Consider this class to be a review for you. So, okay. And all right, so to get connected, I am going to share this link right now with everybody. And I put this in the email. To this, please send a Google Calendar. Oh, I shall. Okay, for the entire course. Good suggestion. I will do that. Google Calendar is really helpful. I don't want to spam everybody on the list who registered, but I'll figure out how to do that in some way, at least. So, okay, so people have access. Okay. So here is, why do I have a Google tag in that? Okay, so here is the link to the chat forum. I'm going to follow it now so you can see what that looks like. Oh, okay. We're working on this. We're going to make this publicly accessible so you don't technically have to log in to see this. But you will need to create an account and log in if you're going to participate in the course. So really strongly encourage you to do that. Zulip is the chat forum, and what it looks like is this. And if you get onto Zulip and you can't find the course, just message me. I'll point you to that direction. Here is the chat forum. This is when it was created. Will recordings be available? Yes. I will post links to the recordings in the schedule, and you can see the link to the schedule. Many of you found this already. I've seen lots of people, joining online. So this is the schedule, and if things change, I'll be updating this live. And be putting the links to the recording in here. Maybe not the same, I'll try to do same day for these recordings, just so, especially since these are Tuesday, Wednesday back to back, so you can quickly catch up if you happen to miss it on Tuesday and wanted to attend live on Wednesday. But this is basically the space where if you're in this space, you can go and create new threads. You can say, I have questions about this. I was trying to prove this and I had trouble. Can somebody help me? I'm having trouble with my installation. And you'll get help from other people in this course. You'll get help from other people in Lean in general, including, so you're just seeing Kevin Buzzard here was helping me deal with, I need to create a new channel. I don't know how, I don't have permission. So he's helping me. And so on. You'll also find the link to join WebEx is here. So that's right there. You have a Lean file, which we'll be getting to in a little bit. Jumping the gun here. But I'll be posting Lean files there as well. I haven't made the one for tomorrow, so I'm going to finish that up tonight, and then we're going to share that as soon as I can. Might be just before class, like this one was. And so those are the links you have there. And then, okay, so getting Lean installed. Here's the link. I shared this in the email. But basically you want to follow the steps in the quick start and install it locally. Locally is best. For this course, you always want to install it with mathlib because we want to have access to mathlib. Technically, you don't need to. Lean is its own programming language. It doesn't require mathlib for you to write programs, but for almost all proofs that you want to write, you'll have to use mathlib. And if you have problems, just ask for help on Zulip. We're happy to help. If this isn't working, you can also run Lean in your browser. There's two websites you can go to. Here's one. And if you need to run Lean in a pinch, I've done this all the time, you can just run it in your browser. And here's Lean. Look at this. You got your, it's basically running VS Code on a server, shipping it to your web browser. You type in code, it automatically gives you feedback to what you're doing. So I had some code for the Boyle's Law proof. I can copy this. I can go to the Lean editor. I can paste it. And now I say, oh, I have all these problems. What's going on? I have all these problems. It's not working. Well, the problem is I haven't given myself the real numbers in this yet. And so this one is resolved when I do import mathlib, but now it should work just fine. Yep. And we get our info view and everything is working in the browser. If your own installation isn't successful and you just are frustrated for a long time and you just need to get it working, you can just work out of this. You can't do multiple files. So if you're actually building a software project and you should be doing that locally for sure, this one can't do multiple files. You can do individual proofs like this though. Mathlib is constantly updated for this. This one always has the latest nightly version of updated mathlib. It's also fun for showing Lean to newcomers. And there's a really cool feature of Zulip. If I just go to some random thing, maths, okay, I'm just going to hop into some random thing on this. You can view in Playground. So, so you can pop out view in Lean for Playground. Here was a suggestion that somebody made. Here, I'm going to help you with your problem, and you can pop that out, and now you have this running in the Lean web editor, and the no goals is coming up. That's a really handy tool, I think, to have, because a lot of people say, well, it's still not working, and it's because their own installation isn't working and it can't keep moving. So, I absolutely should. The Lean file for today. I emailed a half hour before to the whole list of people. I'm just going to say, no, I can't, because we have 10 minutes left to stay in time under 2 hours, and I want to go. It's not a lot of text. Because I guess I can post it in Zulip. But chances are getting it on Zulip is going to be tougher. So I'm just going to drop the text into Web. Oh, but WebEx doesn't copy paste text out very well, so that might actually work for you very well. I'll just drop it on Zulip. Yep, I will update the links in the channel. New topic. This will be Lean files for class. And find the Lean files for class here. All right, and I will then go get that for people. You'll need to go and search for the class. Here we go. You'll need to search for the Zulip topic. I'm just going to move on, but yep, that's the link. That should be it. Okay, and I'm going to move on to our first proof. First, a couple of VS Code tips. Hold your mouse over stuff. you will get so much information from mouse over things, okay? And the other tip is, here's a tip to get the info view back if you happen to accidentally close it. It happens to me all the time. Really frustrated, and then I learned the trick to getting it back. So you can look at those later. But if I wanted to know order of operations, you can put your cursor over the symbol, and you'll see in highlights which things are currently in scope for that. And you can move your cursor around. You can see that, what does the star symbol do? This computes the product. And the meaning of this is type dependent. Okay, well, what is a 3? 3 is a real number here. Oh, interesting. It casted it to a real number. You know, what is y? Y is a real number. And so on. So get information, you know, what are these tactics I'm using? What is ring? Ring is going to tell you all about this tactic. This comes from the documentation. All really helpful stuff. Then this is going to be the main subject of tomorrow. I'm going to give you a taste of it today. These are calculation style proofs about equality. And this comes from Mechanics of Proof, chapters 1.1 and 1.2. We solve problems which feel pretty close to high school algebra, deducing equalities and inequalities from other equalities and inequalities, but we're not using a technique that's usually taught in high school algebra. This is, we're going to build a single chain of expressions connecting the left-hand side with the right. And a brief guide to number systems. N is the natural numbers, 0, 1, 2. Z are the integers. That include negative numbers. The rational numbers include fractions. The real numbers include irrational numbers, like pi square root of 2, that cannot be expressed as a fraction. They also include fractions, and they also include negative numbers. And then we have the complex numbers, which include all of the real numbers plus a complex component of the real numbers. In Lean, these are all accessed as these types. So you can define all of these in this way. And if I wanted to get, you know, I could define X and Y to be complex numbers. I can use /C to get it. How do we type these symbols? I knew it. They're always coming. Okay. So if you the first tip is hold your mouse over the character that you want to do. Then you can see in the mouse over text, type C using /sli, /com, /com, or /bc or bbc. These are all different ways of getting this C character. If you want the real number character, okay, you just do a /r, /real, okay, /n. N turns it into /n. So, oh, this one has such long documentation, it doesn't fit in one mouse over. You need to come in here and scroll down to get the type, the instructions on how to type this. And sometimes you can prove things for naturals that you can't prove for reals, that you can't prove for complex, and so forth. So that's another bit of background that we don't usually hear as scientists and engineers. And the first example that we're going to cover today is this one. And so I got this off YouTube. We have a light plane flies 450 miles with the wind. It takes 3 hours. Against the wind, the plane takes 5 hours to make the trip. What was the rate of the plane? What's the speed of the plane in still air? What was the rate of the wind? And you can listen to that YouTube video teaching the method of elimination is what they're doing. And so X is the plane in still air. Y is the speed of the wind. And so you set it up as the distance traveled is the speed times the time. And we have 450, X plus Y, 3, 450, X minus Y, 3. And so those are translated into these math expressions. So we have a system of equations and we need to solve it. And then this is what they do. Oh no. Proof by elimination. We're taking these two equality expressions and we're adding them together so that we cut out the 15y, and then we solve it to get x is equal to 20 and y is equal to this. This is bad math, okay? This is not a sound technique. And the answer is not wrong, but the approach used to get the answer is not wrong. The reason is what we're doing here. 15x plus 15y equals 2250 is a proposition. 15x minus 15y is equal to 1350 is a proposition. I can't add propositions together. That's not an operation that propositions do. I can do propositions like and. I can say this is true and something else is true. We're going to talk about logic later on. But this is not valid. And I think I learned this too. Like, did you learn? Did you learn how to do the elimination technique when you were learning solving systems of equations? What we're going to do is walk through a rigorous proof of this in a lean file. And to simplify things, let me hide my list of files to make this a little bigger. Okay, so I translated this. So, a dash in lean initiates a comment, by the way. So all of this stuff, none of this is computed, just text you can use to annotate your stuff. So I've defined this. Now, a natural way to set up the problem would be to write an example and have your x and your y and say equation 1 is 450 is equal to x plus y times 3. And equation 2 is 450 is equal to x minus y times 5. And this one's just a little harder to work with. You can solve this in lean. You certainly can. It's just going to be, it's not the structure of the problem I want on your very first lean exercise to walk you through. So a simpler way to set up this problem is to get this times 3 and this times 5 out of here before we define the problem and move the x and the y to the left-hand side, just to make it a little bit easier. Then we have a different example. And what we're doing here is a calculation-based proof. A reminder of what I'm talking about here. Building a single chain of expressions connecting the left-hand side with the right. So what this solution is, I'll just walk through what this looks like, is first we're going to say x is equal to x minus y plus x plus y divided by 2. How do I know this statement is true? I know because I have ring. Ring is a tactic that does algebraic simplification. I simply know that this is true. Lean tells me I don't have a problem here. The next line, you do an underscore, which copies what was done here into the next line. So my next line is going to be is going to simply say x minus y plus x plus y divided by 2 is equal to 90 plus 50. How did I know to do that? Well, I said rewrite. Rewrite is a tactic meaning substitution. And I have this fact, x plus y is equal to 150. And I have this fact, x plus y is equal to 90. And so this tactic was able to figure out where is x minus y and where is x plus y in this. It did the pattern matching to drill down into, this is true. So it believes it, and we've rigorously proven that these are equal. Now I have the statement 90 plus 150 is equal to 120. And this one I can just use ring again. This is an algebraic simplification. There are other tactics that are helpful to use. Num is another thing that can do general basic calculator type math. These have different capabilities. When you're down to numbers, a lot of different tactics close, but if you're more algebraic type expressions, sometimes some of these tactics work, sometimes they don't. we'll get more into that as we dig into these things deeper. But this is a way to set up that physics problem on, how a plane is flying with and against the wind as an exercise in lean. And before we wrap up, I'm going to emphasize this final point, that lean is not yet a computer algebra system. So what do I mean by this? Theorem provers are like lean, Isabel, these tools I've been talking about. These do proofs. They symbolically transform different formulas. You saw that in action, okay? And they're constrained to only perform correct transformations. That's where their rigor comes from. You're not allowed to write a rule that turns, if I have A times B is equal to B times A, sounds like I should keep that, right? It's not always true though. If A and B are matrices, it's not true. So if A and B are natural numbers, then sure, it is true. But I need to prove that's true before I'm allowed to do something like that. And by building them off of a small trusted kernel, then you can trust everything in the library, and there's more rigor going on here. Computer algebra systems include Mathematica, SymPy, MATLAB. These do calculations. They sort of start at point one, and they run and they land at the final conclusion. They are often also capable of symbolically transforming formulae. So when you're doing symbolic math, you can ask Mathematica Wolfram Alpha to solve this differential equation for, solve this quadratic equation for x, for example, and things like that. In this, you have correctness, however, is only really checked by humans. I mean, they have different routines of this, but it's not constrained to only perform correct transformations. The algorithms that they have implemented are not interconnected and built off of a small trusted kernel like theorem provers are. And a big thing I want to emphasize that I'm going to sort of leave you with and revisit on Wednesday and tomorrow is that theorem provers are not built to solve for X. Not really. And I say not yet because there's active work in doing stuff with lean to increase its automation and its capabilities so that it is more useful in this respect. Because notice what we did in this problem. We have the example said, what was the rate of the plane in still air? We didn't solve that question. We stated, assuming this and this, prove that x is 120. I got the answer in the first place. So I got the answer. I needed to state the thing that I'm trying to prove. That's what is very different from a lot of the kinds of problems that we encounter in science and engineering. And so I have a lot of help from my research group. They're doing work to help this class by defining problems for us to solve for this class that have applications in science and engineering. That's going to be our main goal. Is we would have dozens of problems for you to solve and build up your experience practicing these with application problems that have connection to science and engineering, not just arbitrary X and Y math type problems. But it's hard because a lot of the problems are calculation based, and we have to think more differently about how to cast science and engineering questions that we're interested in into problems that can be stated as theorems. And that doesn't mean that it's not useful. It's just you need to think carefully about what we're trying to do and stay tuned, because in the next few years, I think there are going to be more capabilities to get theorem provers to do this kind of thing instead of needing to have the answer afterwards. All right, and before we wrap up, I'm going to answer one last question. As you said, real numbers are not the same as floating. points. If we have a proof of real numbers as physics or something, then we make a proof of a program that calculates something. There's a disconnection. As the proof is of reals and the program uses floating. Is there a subset of reals we should use instead? No. Is what I would say is my perspective on this. It's harder to prove those things about the subset of reals. Floating point numbers are a subset of reals. In fact, they're a subset of rational numbers because I can, if you think of the number of digits, you can write any floating point number as a rational number, actually. But you can't. Our strategy is to say my function operating on floating point numbers is not going to give the same answer as the function operating on real numbers because, I mean, if my function is a square root, right, there's an infinite number of digits in my answer from real numbers, but there's not an infinite number of digits in my answer from a floating point number. So that's not the same thing, okay? But our goal is to build something useful. And we need our programs to be executable in order for them to be useful. I would say the guarantee is that I have written the code, I aim to write the code in a way that bridges this gap so that I'm at least confident the same function is operating on the same realms, even if I've only proven the logic of the function and how it's connected with all the other things in the software for real numbers. Those proofs don't hold for the same functions operating on floating points, but I can use the same floating functions, literally the same floating point functions on those arguments. Thank you, everyone.